Hey, welcome back. We are on our third video, providing some explanation of the questions for 8-20, our second part of our review. This is the written part of the review, 8-20, Test Premier. And we're going to pick back up with question 11. We learned in question 10 how to write this in ionic form. Ionic form just means pull apart the things that are in solution, aqueous. Pull them apart. We did. We pulled apart the copper, the Cu2 pluses from the Cl minuses. We had 6 Cl minuses. 2 times 3 is 6. There they are. On the right side, we still have 6, 2 times 3. We still have 6 Cl minuses. We had a 3 Cu2 plus right here. We had 3 Cu2 pluses. There they are. We had 2 Al3 pluses. There they are. So we wrote this in ionic form. Ionic form doesn't mean you have to be an ion to be in the equation. It just means you have to pull apart the things that are ions in compounds. Now we get to the net ionic equation. The net ionic equation, the word net means only show the things that are changing. Only show the ions that are undergoing a change. You don't show the things that are the same on both sides. So we look at the left side, our reactant side, and we compare it to the right side, and we're not going to write the things that had no change. Here we have 6 Cl minuses. There we have 6 Cl minuses. The Cl minuses did nothing here. They had no change at all in this reaction. We don't write those. Net, they want the ones that changed. So who changed here? On the reactant side, the aluminums were what? They're neutral, no charge. But during the reaction, they became 3 plus and acquired a charge. That 3 plus means that they must have forced something to take 3 electrons off each aluminum for a total of 6 electrons moving. Aluminum is a more active metal than copper. When we started, the coppers were 2 plus. We had 3 coppers at 2 plus. What happened in the reaction? They went neutral. So they went from 3 times 2 plus, there was a total of 6 plus, down to neutral. Over here, where did that 6 plus end up going? Right here. 2 times 3 plus is 6 plus. When you write it in an ionic form, your total charges must be the same on both sides. 3 times 2 plus is 6 plus. 2 times 3 plus is 6 plus. Our total ion charges were conserved or remains the same. So what really happened here? We had 2 aluminums, each getting rid of 3 electrons for a total of 6 electrons moving. We had 3 coppers at 2 plus. We had 3 coppers at 2 plus. Each copper took 2 electrons and went back to neutral and precipitated out a solution. And now they're going to want us to show that happening in a drawing. We're trying to show what happened in a drawing right here. We go back up. They told us to illustrate what happened, not the net ionic equation. They wanted to show the whole thing, which is best seen in number 10. So number 10, on the reactant side, we have 2 aluminums. So on the reactant side, we need 2 aluminums. There they are. There they are. And we need to add the 3 valence electrons that are going to be forced onto the coppers for each of those. That's the S side. There's the 2 in the S. There's the 1 in the P. There's the 2 in the S. There's the 1 in the P. What else did we have here? We had 3 Cu2 pluses floating around. There's one of them. There's the other one. There's the other one. What else did we have floating around? We had 6 Cl minuses floating around that did nothing. Where are they? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What happened to them? Nothing. There was no change to them. They were 6 Cl minuses on the reactant side, and there were still 6 Cl minuses on the product side. There they are. 1, 2, 3, 4, 5, 6. They did nothing. The Cl minuses you need to label as the spectator ions. So what really happened in the reaction, as we've talked about? Active metals will force less active metals to take the electrons. The copper 2 pluses say that they can take 2. So this aluminum has 3 to get rid of. It gives 2 to that copper. This copper can take 2. It gets 1 from this aluminum and 1 from the other aluminum. So this electron right here is going to that copper. This electron right here is going to this copper. I have one more Cu2 plus. This active aluminum will force that one to take both of those electrons. So what happened to the coppers? They had, on the reactant side, they were positive, 2 plus each. So they were able to stay in solution. But during the reaction, the aluminums forced electrons on it. So this copper right here now has 2 electrons. This copper right here now has 2 valence electrons forced back on it. This one has 2 valence electrons forced back on it. They went from 2 plus back to neutral. When they're neutral, they precipitate out of solution. Those 3 copper ions that are now back to neutral, they're no longer ions, they precipitate out. This aluminum right here got rid of 3 electrons. It's now 3 plus. This aluminum right here got rid of 3 electrons. It's now 3 plus. It has a charge. So water can still hold it in solution. And there's our drawing illustrating what happened in this single displacement reaction, an active metal forcing out a less active metal from solution. We're going to move on now to the next page of our review. And on this one, we're going to be dealing with precipitation reactions, double displacement reactions. And in this one, we have to predict. They're asking us to predict what's going to happen in the reactions. If a chemical reaction occurs, we're supposed to complete the reaction and balance it. If a reaction cannot happen, then we write no reaction. Now, you have to recall that in a double displacement reaction, for it to happen, one of 3 things must occur. There's 3 things that must occur. One of them was the formation of a gas. A second thing is the formation of a liquid, water. Formation of water. The third thing is the formation of a solid precipitant. Something that water cannot pull apart. Double displacement reactions must occur aqueous. They must be in water so that ions can interact. If gas is a product, it'll bubble out of solution. If water is a product, as in an acid-base neutralization reaction, which is a type of double displacement reaction, once you form the water, it takes those ions out of play. And the third thing is the formation of a solid precipitate that comes right out of solution. To know if a precipitate comes out of solution, you need a solubility chart. And there we go. So in this first reaction, we have ammonium chloride, NH4Cl. Where did we get that formula for ammonium chloride? NH4 is 1 plus. Chloride is 1 minus. It's a halogen, crisscross, 1 plus, 1 minus. We have lead 2 nitrate. Nitrate is NO3 minus. It's 1 minus. The lead here is 2 plus, crisscross. The 1 minus from the nitrate goes there. The 2 plus from the lead goes right there. We've got our formula. Now, are they both aqueous? We have to come up to the chart. Is ammonium chloride aqueous? Here's ammonium. There's chloride. Ammonium chloride is aqueous, as we see right there. What about lead 2 nitrate? We've got to find lead 2. There it is. We've got to go over to the nitrate column to make sure that it would stay aqueous. Here's the nitrate column. We go down to lead. Over. Yep, it could be aqueous. So aqueous means water is going to pull these salts apart. They're floating around. The NH4, in a double displacement reaction, the first thing here is going to end up with the second thing there. So ammonium is going to exchange places with the lead. The positive ions trade places. NH4 ends up with NO3. There they go. There's the NH4 and the NO3. Ammonium ion is 1 plus, as we learned long ago. The nitrate ion's 1 minus. Will that precipitate out of solution? Here's ammonium. We go down to nitrate. On this chart, it says AQ. What does that mean? On this chart, AQ means it's aqueous. It will stay dissolved in water. So that will not drive this reaction. But what about the next product? The lead 2 plus ions are going to bump into the Cl minuses in solution. They're going to bump into each other. The lead is 2 plus. The iodide is 1 minus. Crisscross. PbI2. What's going to happen here? We go back up to the lead. There it is. We go over to the iodide column right here. Is the iodide column. There's an S there. S means what on this chart? On this chart, S means it's a solid. It will not stay dissolved in water. It's going to precipitate out of solution. That is one of the 3 factors that is met. Right up here, we're going to form a solid precipitant. There it is. That reaction will happen. What about our next reaction? Potassium sulfate. Where did they get this formula? K2SO4. We learned long ago that the sulfate ion is 2 minus. Potassium is an alkali metal, family Roman 1. They only have 1 electron to lose, so they're always 1 plus. Crisscross, the 1 down to the sulfate, the 2 minus down to the potassium, K2SO4. They wrote aqueous next to this. Is it aqueous? We come up to potassium. There's potassium. We go over to the sulfate column right here. Potassium sulfate is able to stay in solution. Water can keep them pulled apart. Here's calcium chlorate, Ca, alkaline earth metals, family Roman 2. They're 2 plus. That's where this 2 came from. They crossed the 2. The chloride ion we learned long ago was ClO3. It's 1 minus. That is why there's no subscript after the calcium. It's only a 1, and when it's a 1, they don't write it. They wrote an AQ after calcium chlorate. Is it actually AQ? Here's calcium. We go over to the chlorate column. There's the chlorate column. It is aqueous. So that means in this solution, if they pour these 2 solutions together, the K pluses are going to bump into the ClO3 minuses. Are they going to precipitate from solution? We come back up. Potassium. Over to the chlorate column. No, they will not precipitate out of solution. They will remain in solution. That's not going to be a driving force. Potassium, as we learned, is 1 plus. The chlorates, as we already talked about, is 1 minus. We will have K pluses and ClO3 minuses floating around. But what happens when the first thing here bumps into the second thing here? Remember, in double displacement, the Ca is going to trade places with the SO4. So now we have CAs bumping into SO4s. Here's the CAs. Here's the SO4s. It says solid right there, which means it's going to precipitate out of solution. We will end up with a solid precipitate here. That will drive this reaction to happen. We mentioned calcium's an alkaline earth. They're 2 pluses. They have 2 valence electrons. Sulfate's always 2 minus. Crisscross, reduce. CaSO4. We have 2 chlorates here. We have 2 potassiums here. We need a 2 in front. In this reaction, we had 2 iodides there. We're going to need, holy crap, hold on. I certainly hope you guys caught that little mistake. I had chloride here, and for some reason I wrote iodide over there. That's potassium chloride. Let's make sure that that's still on number 13. Here's the chloride column. We go down to potassium, or we go down to lead, lead 2. Chloride column. Lead 2 chloride is insoluble. There's our lead 2. There's our chloride. So that would still precipitate out of solution. I'm glad we went back to double check to make sure it was balanced. 2 chlorides there. We need a 2 in front. That gives us 2 ammoniums. There's my 2 ammoniums right there. That gives us 2 nitrates in front. 2 right there. We're good to go. That takes care of going back to make sure 13 was balanced and corrected. And we go to 14. And we have 14 completed as well. 1 calcium, 1 calcium, 2 chlorates, 2 chlorates, 2 potassiums, 2 potassiums. And that concludes our video, and we will pick back up with our next video, number 15.